Thanks everybody for coming. It's really a pleasure to introduce Chris Shallue. As many of you know, he's been working on his thesis here. Completed a very interesting document. So Chris actually came to us from a somewhat unusual background. He had done his undergrad degree at Monash in mathematics, taking very little physics, and then had gone off to Google to work on machine learning and publishing in the machine learning literature for 5 years. And then I think somehow got entangled with Andrew and working on exoplanets, applying machine learning to exoplanets. I think that got him a little bit of a bug for astronomy. He applied to us and maybe some other places, I don't know. But we thought this was an interesting opportunity. And so and Chris came, I guess, a little over 5 years ago. Of course, he had almost no undergraduate physics. So he spent his first year here doing undergraduate physics as a crash course, and then switching into graduate physics and graduate astrophysics. He started working with me on cosmological surveys, but after about, I'll say 3 years, decided that he wanted to work more on the topics, sort of fundamental physics and sort of deeper questions, particularly with regards to gravity. And so he sort of had to have a real search for how to actually find an interesting project in that area. And in particular, because our department didn't have a ready-made advisor on this, he went off and really engaged himself at the Black Hole Initiative to try to meet people there. I think that's where I primarily met Jacob. And then found Sean Carroll, who was has been able to supply part of the project that he's worked on here. So Chris really had to make his own path for the PhD, sort of knitting together advisors from beyond the department, and I think has completed a really interesting set of work in that area. So without further ado, I'm going to turn it over to Chris to tell us about his work, and then so after this will go for maybe 45 minutes or something, and then as many of you know, then the committee and candidate retire to a room on the other side of the CFA for a private defense, and we'll be hopefully finished somewhere around lunchtime. Thank you.
Cool. Thanks, Daniel. Yeah, thanks everybody for coming. It's great to see so many familiar faces here. Today I'm going to be talking to you about the work I've been doing in the last 2 or 3 years of my PhD here. And it's going to be about measuring Hawking radiation with particle detectors and cosmological surveys. So the talk is going to be split into 4 parts. I will start with some brief background on black holes and Hawking radiation. Then I will talk about what Hawking radiation looks like as you fall into a black hole. The third part of the talk will be about signatures of evaporating primordial black holes in the cosmological structure. And I will end with some acknowledgements. So since we have a mixed audience here, let me just briefly give some background. So this is a real photograph of a black hole. It's the supermassive black hole at the center of M87, a galaxy about 50 million light years from Earth. You can see that there is a bright ring of light. This is light from the accretion disk of dust and gas orbiting the black hole. So the black hole is this central dark region in the middle. And a black hole, it's a region of space-time with such strong gravity that nothing can escape. The boundary of this region is called the event horizon. I've shown the approximate location of the event horizon with this white ring. And anything that enters inside the event horizon can never escape, no matter how much force is applied to it. The gravity inside the event horizon is simply too strong. So for the remainder of the talk, I'm going to be using the simplest model of a black hole called a Schwarzschild black hole. It's named after Carl Schwarzschild, who first discovered the solution to the Einstein field equation that describes this sort of black hole. He did this famously while serving in the German army during World War I. So a Schwarzschild black hole, it's a model of an uncharged, non-rotating black hole in empty space. So in particular, there will be no accretion disks in any of the black holes that I talk about in the remainder of the talk. So the Schwarzschild black hole is a classical solution to the Einstein field equation. And when I say classical, I mean that it doesn't, it arises in a theory of physics that doesn't include quantum mechanics. However, our best models of matter in the universe incorporate quantum mechanics, in particular quantum field theory, which is the quantum mechanical theory of fields. So in quantum field theory, each type of particle corresponds to a field. So there's an electron field, there are quark fields, there's an electromagnetic field. And particles correspond to vibrations in those fields. So a vibration in the electron field is an electron particle. A vibration in the electromagnetic field is a photon, which is a particle of light. And in quantum field theory, the notion of empty space actually gets replaced with a different notion called the vacuum state. So in quantum field theory, the fields are always there throughout space, even when there are no particles. Instead, we would say that the field is in the vacuum state, the vacuum state corresponding to no particles. But nonetheless, in quantum field theory, space is not empty. So what happens when we model a black hole, not in classical empty space, but in a space filled with quantum fields? So Stephen Hawking considered this question famously in 1975. He set up a model for a star collapsing to form a black hole in the presence of a quantum field in the vacuum state. So because it was in the vacuum state before the star collapsed into a black hole, there were no particles in the quantum field. But what he found was that after he modeled the star collapsing, space-time was then divided into two regions, the region inside the black hole, the region outside the black hole. And the quantum state was also divided into two regions. And it turned out that from the perspective of observers located very far from the black hole, the object actually looked like a glowing thermal object that was radiating particles, and it had a temperature. And that temperature is now called the Hawking temperature. In Planck units, the Hawking temperature of a black hole is 1/8 pi m, where m is the mass of the black hole. If you go to Stephen Hawking's grave in Westminster Abbey, you will see this equation engraved on it. And so this image of a black hole I'm showing on the left, I'm not actually using the orange light to represent an accretion disk, but this is actually reflecting the fact that, according to quantum field theory, black holes themselves glow. So if you're just hearing about Hawking radiation for the first time, you may have some questions about it. And there are, in fact, many open questions about Hawking radiation. And the reason for this is that Hawking's derivation was not the full story. Hawking used an approximate theory in which he combined classical general relativity with quantum field theory. But we believe that there is a deeper, more accurate theory of physics in which space-time itself is quantized. That theory is called quantum gravity. And so without a complete theory of quantum gravity, which we don't yet have, there actually remain some questions that we don't know the answer to about Hawking radiation. So let me just give you a brief taste of some of those questions. Firstly, where does Hawking radiation originate? So does it come from right by the event horizon of the black hole, or is it generated in some region outside the event horizon? How is it generated? What is the exact microphysical process that generates the particles? There is a famous paradox called the black hole information paradox that is a very open and important problem related to Hawking radiation. And it concerns the question of what happens to the information about an object that collapses to form a black hole and is then transformed into Hawking radiation. Is the information about the original object lost? This is an open paradox. And finally, what would happen if you fell into a black hole? So this almost sounds like a sci-fi question, but there's actually been a lot of interest in this question in the past 10 years. There is a hypothesis out there at the moment called the firewall paradox. The firewall hypothesis that says that if you fell into a black hole in a proper, accurate theory of quantum gravity, there would be a high-energy firewall surrounding the black hole, and you would be incinerated as you fell in. This is an open hypothesis that has been discussed a lot in the past 10 years or so. So as I said, the true answers to all of these questions may need to wait until we have, a proper theory of quantum gravity to model Hawking radiation. But nonetheless, we can still try and make progress in these questions, even though we may not be able to answer them exactly, by using semi-classical methods like in Hawking's original derivation. So that's the sort of framework in which I'm going to be working. Okay, so the first main part of the talk is what Hawking radiation looks like as you fall into a black hole. So this is joint work with Sean. I should have the paper up online in the next day or two, so keep an eye out on arXiv. And the basic idea of what we are trying to do is to measure the Hawking radiation near the horizon of a black hole. And so in simple terms, we're trying to take a camera and drop it freely into the black hole and take some photographs along the way. By studying the images that the camera takes as a function of the radius, we can see hopefully how the Hawking radiation is going to change as you approach the horizon and fall in. So in a little bit more technical detail, we don't send in a camera, but we send in something called an Unruh-DeWitt detector, which was originally proposed by Unruh and DeWitt in the 1970s in order to study Hawking radiation. And it's basically a simplified model of an atom. So it has two energy states, 0 and E, a ground state and an excited state. And technically, we're going to linearly couple this detector to the scalar field. And we will control whether the interaction between the atom and the field is on or off by so-called turning on and off the interaction. And what we do here is technically we change the coupling constant to the scalar field. And we do this over a time interval, which I'll represent by delta tau. This will be important. You can think about this time interval as like the exposure time of the camera. If during the exposure time, the detector transitions from the ground state to the excited state, we interpret this as a particle being detected. You may be familiar with this. It's analogous to an atom absorbing a photon and jumping from one electron orbital energy state to a higher energy state. And if you work through the mathematics of this, then it turns out that if you send in many detectors, the number of particles detected has a formula. There is a proportionality constant lambda, which I won't worry too much about. It depends on the details of the detector. And then there is this function f, which I'll call the response function. And this is a function that depends on the energy, and it depends on the exposure time, and it depends on the trajectory that the detector follows. But the important thing here is that we can calculate this thing directly. And so the task of taking these photographs, theoretically, boils down to computing this function f. It turns out, unfortunately, that computing f is very, very challenging. There are some simplified situations like lower dimensional spacetimes and special classes of trajectories where it can be done exactly. But in fact, in a more complicated situation like falling into a black hole, it has to be computed numerically. And it's a real pain. And actually, a lot of the work that I'm going to that went into the results that I'm going to present actually just come from figuring out how to numerically calculate f. But for now, let's just proceed by remembering that f is proportional to the number of particles detected, and I'll just show you the results of these calculations. Okay, so let's look at the response that would be measured by an infalling Unruh-DeWitt detector. So this is how it looks. So what I'm showing here is the response at 3 different detector energies, and I have a detector falling into a black hole from the right of the screen to the left of the screen. R is the distance from the center of the black hole, and the horizon is shown here in black. So anything to the right of the black line is outside the horizon, anything to the left is inside. And I'm showing here F on the y-axis. The numbers are not super important because remember, this is just proportional to the number of particles detected. But what is important is the trend. So perhaps the first thing to note is that the numbers are positive. And so this suggests that the detector is detecting particles. So it appears as if we are detecting the Hawking radiation. You can also see that there is a very clear trend as you go from the right to the left. As you get closer to the black hole, you are actually measuring more particles, right? It seems as if the amount of Hawking radiation is increasing as you get close to the horizon. And interestingly, it seems to be increasing even once you are inside the horizon. Finally, I will note that there do not seem to be any local features other than the broad trend. So there is one other paper that had purported to compute this in the past couple of years, and they actually found that there was a bump near the horizon, a local feature in the Hawking radiation, and that might suggest there was something special or interesting going on at the horizon. In my results, I don't see anything of that sort. So it seems, at least according to these calculations, that the horizon is locally unremarkable. And it's just part of a broader trend in the measurements. But actually, in order to understand these measurements properly, we need to understand a bit of a subtle behavior about how these detectors work. And that is the exposure time. How does the exposure time affect the results? So in each of these results here, I've made a measurement over a small enough exposure time that the detector didn't move too far, so that I could actually place the point in a specific location. But what is the effect of choosing that exposure time? So in order to understand this, let's dispense with black holes for a moment. And let's just study what happens if I take one of these particle detectors and I put it in a pure thermal state at a fixed temperature. And I measure the response of this detector at different exposure times. So I understand the dependence of what the measurement yields as a function of the exposure time. And so this is the result that you get. So as a function of the exposure time now on the x-axis, you can see this interesting shape, right? On the far right-hand side, the response that you measure is proportional to the exposure time. I know this is a log-log plot, but this is actually linearly proportional. And this makes total sense because the longer you expose the detector to the field, you should measure more particles, or you should have a higher probability of measuring particles. On the left side, though, there is a more unexpected behavior where the response actually asymptotes to a constant value, no matter how short the exposure time is. This actually arises because of the way that we have modeled this as a time-dependent interaction term in the Hamiltonian of the system. So if I set up a time-dependent coupling constant in a quantum Hamiltonian, and I change that interaction term too rapidly, right, that can actually cause excitations in this case, the detector, right? And that is what is sort of dominating the output on the left. And so on the left side of the plot for short exposure times, what the detector measures is actually more dominated by the effects of this switching and not actually by detecting the Hawking radiation particles. On the right-hand side of the plot is where you want to be, because that now you're more sensitive to the actual particles in the field. And so why is this particularly relevant in this case? Well, it turns out that the exposure time that I need in order to make a localized measurement near the horizon is short. It is over here, and there is really no way to get around this. if you want to have a detector freely falling into the black hole, there is really no way to make a measurement over here, right? Because the detector is simply going to move too far, and you'll no longer be able to localize with very granular resolution exactly where those particles were detected. And so a simple takeaway from this analysis is that a detector freely falling into a black hole does not have enough time to measure Hawking radiation, unfortunately. So this seems like a problem for the results that I showed before. But we can fix this problem, or we can at least gain some useful insights from the results if we just change our mental model a little bit. So all we need to do is we need to stop thinking about the Unruh-DeWitt detector as a camera and instead think about it as a thermometer. So in what we're going to use the detector for now, we're going to do the same measurements, but we're going to interpret the measurements as giving us an indication of what the local temperature of the field is, because we can't really interpret its measurements as detecting Hawking radiation particles. So to do this, I just make a simple definition. So I define the effective temperature measured by an Unruh-DeWitt detector. So to be the temperature of a thermal state at which the detector would record the same response. So basically, I'm going to match the response that is produced in the black hole space-time with the response that is produced in a thermal state, and I'm going to pick the temperature of that thermal state so that the responses of the particle detectors match. And then I'm going to say that that is the effective temperature of the black hole at that location. If we do this, it actually turns out to be quite interesting. So I'm showing a very similar plot to before, but now I'm replacing the y-axis instead of the response with this effective temperature in units of the Hawking temperature. And it turns out that if you do this, all of the energies line up. They all give a consistent local temperature. And it actually even remains consistent if I choose a different exposure time, if I go larger or smaller. So what we see is that far from the black hole, the local temperature appears to be approaching the Hawking temperature, which is exactly what you would expect. But the local temperature does increase as I go towards the horizon. It actually goes almost exactly through 2 as I cross the horizon, and then it continues to increase inside. The really interesting thing about these numerical results is that they match almost exactly with this formula that has appeared previously in the literature that was derived through completely different independent means with a very sort of heuristic argument even. So the way that this formula was derived was that the authors took the Schwarzschild black hole in 4 dimensions, embedded it into a higher dimensional Minkowski space, and then computed the acceleration of an observer in that space and used that to assign to the trajectory an effective temperature. So this is like just very different, very independent, and even in some sense more heuristic, right? And so the very, very close agreement between my results, which are quite numerically exact, and these other results, which are approximate, suggests that there might be cause for further investigation of these higher dimensional embeddings to understand what's going on with Hawking radiation near the horizon. So let me now pivot from more theoretical calculations to more practical ways we could potentially measure Hawking radiation. And so this third part of the talk is joint work with Julian and Gordon. You can find our paper online. Okay, so I've been talking about black holes emitting particles, right? If they emit particles, these particles have energy. We expect those, the energy emitted from the Hawking radiation to correspond to energy or mass energy being lost from the black hole. And this means that as the black hole radiates particles, it's expected to lose mass over time, and eventually it will evaporate. Now, as you can see in this animation, the final stages have resulted in an explosion. This is actually what we expect to happen, because if you remember, the Hawking temperature was inversely proportional to the mass of the black hole. So as the black hole is losing mass and shrinking, it's getting hotter and hotter and hotter. And so the final stages of the lifetime would be expected to be a very violent burst of energy, like an explosion. But this may be surprising, because we actually have detected many black holes in our galaxy, and we haven't seen any of them explode yet. So why is that? Well, it turns out that because the black holes that we know about are all solar mass or greater, these black holes have very, very low Hawking temperatures. And correspondingly, their luminosity, or the amount of energy they output per unit time, is very low. And so they are not going to evaporate for 10 to the 65 years, right? Which is way, way longer than the current age of the universe. So if we actually want to observe black holes evaporating and exploding, there needs to be some kind of black hole that has a smaller mass. So, for example, if I had a black hole that was 1 ton, it would have a very, very high temperature of 10 to the 20 Kelvin. Its luminosity would basically match the luminosity of the sun, and it would evaporate completely within like less than a nanosecond. The question is, where are we going to find black holes like this to study? So actually, since the 1960s, it's been hypothesized that a population of black holes may have formed in the very early universe, called primordial black holes. And unlike the black holes that we know about in the present universe that all have masses greater than the mass of the sun, primordial black holes could have had a very wide range of masses. And in particular, they may have had very small masses where Hawking radiation was significant. In particular, any primordial black holes with mass less than around 10 to the 8 grams would have evaporated before Big Bang nucleosynthesis, which is the moment in the early universe where the first atomic nuclei formed. This is also the earliest moment where we have direct observational data from is Big Bang nucleosynthesis. So if these black holes evaporated before then, it would be very hard to detect this, and therefore the abundance of primordial black holes with these masses is basically unconstrained by current observational data. In particular, if their abundance was sufficiently large, the early universe would have gone through a period where these black holes actually dominated the energy density, and then they evaporated. But even if they did that, evaporated before Big Bang nucleosynthesis, it would be very difficult for us to detect this scenario. So if this happened, how could we possibly detect it? Well, it turns out that Hawking radiation produces all particles that exist in nature. And this may include particles that we have not yet discovered. So in particular, in this work, I considered a so-called Hawking relic, which is a stable, non-interacting type of particle that may have been produced by evaporating primordial black holes. And because it's stable and non-interacting, we expect that these would have survived to the present day, and we could potentially detect them. If this relic exists and is massive, then it contributes to the dark matter. So for those of you who are not familiar, about 90% of the matter in our universe is a type of matter that does not interact with the familiar baryonic matter that we are made out of, except through gravity. And the Hawking relic would fall into this category and be a component of it. So we know that the dark matter was actually played a very significant role in shaping the structure of the universe today, from galaxy clusters to superclusters and the cosmic web. And so if a Hawking relic was a component of the dark matter, we can potentially detect its presence in the dark matter through its influence on the large-scale structure of the universe as it evolved. So at this point, you might wonder, well, could the Hawking relic be all of the dark matter? And the answer is, maybe. That's a good question to ask, but that has already been ruled out. This situation has already been considered. It turns out the Hawking relic would be too warm, and we know that most of the dark matter in our actual universe is cold. So you should think about these Hawking relics, as I proceed through the rest of the talk, as just being a sub-dominant component of the dark matter. So the way that we model the effects of a Hawking relic on the large-scale structure is through its velocity distribution. So the key piece of work in this project is to model the right from the moment that primordial black holes formed through the time they evaporate, and then through the evolution of the universe to today, what is the resulting velocity distribution of these Hawking relics? And so the answer is it looks something like this. So what you can think of this plot as just being the number of Hawking relics as a function of their velocity in the present day universe. This is a specific example of a particular Hawking relic of a particular mass. This capital omega on the y-axis means the energy density. But because these relics are non-relativistic, it's proportional to the number density. So in order to give you a point of comparison, here is the velocity distribution compared to a so-called Hawking relic. So, a thermal relic. So you should think of this thermal relic as like a neutrino. So the neutrinos in the standard model were originally in thermal equilibrium with the standard model plasma in the very early universe, and then at some point they decoupled. And after they decoupled, they streamed freely through the universe. This thermal relic here is like a new type of neutrino, hypothetical, just for point of comparison, that would have decoupled from the standard model plasma in the early universe. And the key point here is that the thermal relic has a much narrower velocity distribution, which is interesting because the Hawking relic is actually emitted from black holes in a sort of thermal-like distribution. So both of these should actually have fairly similar velocity distributions, you would think. There's actually two reasons why the Hawking relic has a wider velocity distribution at the present day. The reason that it has a wider distribution at the low velocity or the low energy side of the distribution is that the universe is expanding while the black holes are evaporating. So any particles that are emitted early in the black hole lifetime are going to lose energy as the universe expands. Relative to the Hawking relics that are emitted late in the black hole lifetime, they will have lost some energy, and that corresponds to a low velocity tail. On the higher end, this comes from the fact that the black hole temperature is increasing during evaporation. So as the black hole approaches the end of its lifetime, it's emitting increasingly more energetic particles that end up having higher velocities today. So this is actually a fairly distinctive velocity distribution that arises specifically because of the properties of Hawking radiation. And it's distinct from other types of velocity distributions that you would encounter in other cosmological scenarios. So once we have this specific velocity distribution, we can now model how that affects the large-scale structure of the universe as it evolved. So what I'm showing here is the effect of 3 different Hawking relics with 3 different masses. And I'm showing the ratio of the power spectrum, the matter power spectrum, of the universe that includes the Hawking relic to the standard lambda CDM universe that does not have a Hawking relic. If you're not used to looking at power spectra, a quick note is that larger scales are on to the left of the plot and smaller scales are to the right of the plot. So on this particular plot, scales over here correspond to roughly galaxy cluster size scales. The way you can think about this ratio on the y-axis is that if it is lower, there is less gravitational collapse, and if it is higher, there has been more gravitational collapse on the specific scales. So what's happening here is the Hawking relic is actually resulting in less gravitational collapse on smaller scales, but it actually doesn't have very much of an effect on the larger scales. The reason for this is that it has these velocities that are higher than the rest of the dark matter, which is cold. It doesn't have these velocities. And so if smaller regions are trying to collapse, these Hawking relics have high enough velocities to escape from these smaller regions. And so it will be more difficult in a universe with Hawking relics for smaller scale structures in the universe to collapse. And the amount of suppression, or the amount that this decreases, is going to increase the larger the mass of the Hawking relic, because the larger its mass, the larger its fraction of the overall dark matter. So this actually corresponds to a signature. This is a prediction. So we can actually measure the power spectrum using data from cosmological surveys. And we actually have now two different outcomes to compare. If we have the standard lambda CDM model, and we have the model with the Hawking relic. And so if we were to detect less collapse at smaller scales than we expected, that could indicate that there was a Hawking relic present. The question is, can we distinguish that signature from other types of relics, such as the thermal relic I showed before? The answer turns out to be yes, but it will require very high precision measurements. So I'm showing here in these gray lines the suppression that would be caused by the closest thermal relic to each of these Hawking relics. And you can see that they actually have these thermal relics, like the neutrinos, can have a similar effect in suppressing the power spectrum, but it's not exactly the same. And the reason it's not exactly the same is just because of those different widths of the velocity distributions. It just means that it will have a slightly different overall effect. And so this means that, the first step potentially would be, to identify the presence of a relic, right, through some suppression in the power spectrum. That's in some sense the easier part, because you could potentially just see a fairly large dip. The harder part then, which would require very high precision measurements, would be distinguishing the Hawking relic from the thermal relic. But this is in principle possible. So finally, I used these calculated effects on the matter power spectrum to compute constraints on Hawking relics. So as I said before, previous studies had considered, could these Hawking relics be all of dark matter? And they all came up with the same answer, no. But what I asked is, how much of the dark matter could they be? And so I came up with this plot. And so what I'm showing here is the so-called Hawking relic parameter space. So what I have on the y-axis, the mass of the Hawking relic, the mass of the particle. On the y-axis, on the x-axis, sorry, is the initial formation mass of the primordial black holes. And I have derived these solid lines, which are upper bounds. So there's 3 lines for 3 different types of particles: scalar, vial fermion, and massive vectors. And for each of these particles, this area above the solid lines have been ruled out because they would have caused too much suppression on the matter power spectrum. In particular, these dotted lines represent the scenario where the Hawking relic is all of the dark matter. So we already knew that was ruled out. So these results confirm that. These bounds here correspond to roughly 2% of the dark matter. So it's possible that there can be Hawking relics found in the dark matter, but they can't account for any more than 2% of it. And so all of this parameter space under here is still viable. There is another transition that occurs down here in these dashed lines. If the mass of the relic is small enough, the relic will actually still be relativistic even at the present day. So it will actually not be so much a form of dark matter, but a form of dark radiation. So that is the transition that occurs here. But all of this parameter space down here is still viable. Okay, so that's the end of the science. So let me just briefly finish with some acknowledgements. So first of all, I've been incredibly fortunate to have 3 exceptional advisors in my time here. As Daniel said, he was my advisor for my first 3 years here. I really enjoyed working with him. I really appreciate his mentorship. A lot of that time, I would say a year and a half of that time, we were located in different continents. And so our regular meeting time was something like 6 a.m. Boston time and 10 p.m. in Melbourne time. So I appreciate him getting up early and always having a lot of time for me and his other students, even though he's obviously very busy. Julian, who unfortunately was not able to make it today, he's now a professor in Texas and he had to teach today. But he has been one of my advisors in the last couple of years. I've enjoyed working with him tremendously. I've learned a lot from him. And I think one of probably the best weeks of my PhD was when I went and visited him in Austin. We got to work together for a week. And third, Sean, who traveled here for this from Baltimore. I've had a wonderful time working with Sean. If you know a little bit about Sean, if you've read his books or listened to his podcasts, if you haven't, I would highly recommend you doing so. But for those of you who have, would understand that Sean is one of the best people to talk physics with. So I've had a wonderful time working with Sean. Finally, the rest of my thesis committee has been more than just a thesis committee. They've really been additional advisors to me. Jacob, I first met while I took his general relativity class, which I then got the privilege to be his teaching assistant for this year. Some of our students are here. Thanks for coming. But Jacob was the one who first introduced me to the problems and paradoxes that exist with Hawking radiation and some of the more thorny philosophical questions in physics. So he's had a big influence. Ramesh and Peter have also been tremendously generous in offering their time to meet, one-on-one on a regular basis to give advice and guidance, and I really appreciate that. Andrew gets his own slide. As Daniel already said, I think Andrew is probably the biggest reason that I'm here. If I had sent an email to a different person, I probably wouldn't be here. But when I had this idea that I wanted to use machine learning to discover exoplanets, Andrew was the one I found and emailed, and that was almost 8 years ago. We've worked together and been good friends since that time. So he deserves a lot of credit for me being here today. My family as well. My mum has traveled halfway around the world for this. So my sister, dad, and brother are all watching or will watch the recording at an appropriate time. All the other grad students here at the CFA, it's been great to be here, spending these 5 years with you. Probably the highlight was this trip to Arizona to learn about telescopes. shout out to my office mates, Gus and Alexia, over the past 5 years. As you can see, we spent some time on Zoom because of the pandemic. Big shout out to Courier House. I'm a resident tutor at Courier House, which is one of the undergrad dorms here, across the road actually. And that's been one of the most rewarding parts of my time here at Harvard. I'm not moving out immediately, which is nice. But the relationships I have with the other tutors and the students has been very special. And finally, just all the friends and connections I've made while here. And you know, everybody, yeah, sorry. Mariam's laughing at the Photoshop. But yeah, I didn't have photos of everyone. Unfortunately, I don't take enough photos with all of my friends, but I appreciate all of your support in the past 5 years. So yeah, I will just leave with summaries, and happy to take any questions.
Okay, yeah, let's have some questions. The committee's probably gonna be quiet, so you should feel free to ask. There.
On your slide with the dark matter constraints, there's a kink at the right-hand side.
Yes.
What's that from?
Very good. Let me go back to it. So Andrew has noticed this kink here. So this actually has to do with when the black holes evaporate. So the larger black holes are going to take longer to evaporate. So they will evaporate later on in the universe. So early on, when the temperature is very hot, the universe is radiation dominated, not very much is happening. Everything sort of scales very nicely. There is a very simple relationship between the energy density of the universe, the scale factor, and the temperature, right? But things start to go, as the universe cools down, a few interesting things start to happen. So the first thing that starts to happen, which is actually around here, is that the top quarks annihilate and become non-relativistic. And this causes the relativistic plasma that there's a standard model to lose some degrees of freedom. And this is going to modify the relationship between the temperature and the energy density as some degrees of freedom are lost. But you can't actually see those kinks. The big kink here comes from the QCD phase transition, which is the time when quarks became confined into hadrons. And at that time, there was a big, fairly sudden drop in the number of degrees of freedom of the plasma. And so that caused a sort of almost discontinuity in the relationship between the energy density and the temperature. And that basically shows up there. Yeah. Yes.
So on your previous section,
yeah,
you were talking about the detector freely falling into the black hole. As a non-physics person, maybe this is a silly question, but is the fact that it's freely falling some assumption that you have to make? Because my understanding was that was why you kind of had to do your like thermometer camera swap. And so like instead of it freely falling, could you do something where you just have it like, you know, orbit or like slowly fall instead of a free fall?
Yeah, so that's a good question. So why am I dropping this detector into the black hole freely if it doesn't have enough time to make measurements? Okay, so in general relativity, the non-accelerating observers are the ones that are falling freely with gravity. Right. So if you do anything that tries to oppose gravity and change your trajectory, you will be accelerating. You'll have to fire a rocket. So if, let's say I wanted to have a detector sitting outside the black hole and just hovering like just outside the horizon, and then I have lots of time to measure the Hawking radiation. In order to do that, I would have to fire a rocket, to away from the black hole to prevent falling in. And so then that detector, that observer, would be accelerating. It turns out that accelerating detectors will detect particles. This is known as the Unruh effect, the same Unruh from the Unruh-DeWitt detector. Actually, this effect was first demonstrated in the same paper that the Unruh-DeWitt detector was presented. So if I have a detector just outside the horizon that is accelerating in order to stay there, then it's going to be subject to the Unruh effect. And now its detections are going to be dominated by the Unruh effect and not by Hawking radiation. You also mentioned orbiting, and that is actually a good question because orbits are inertial. You don't need to accelerate to be in an orbit. Unfortunately, in general relativity, the closest stable orbit to a black hole is around 2 Schwarzschild radii away. It's actually not possible to have a stable orbit inside 2 Schwarzschild radii. So unfortunately, you can't even set up a stable orbit and look at an inertial observer that way. So really the only way to do it is to have an observer freely falling in. It's an interesting question that you could potentially have the observer fall in at an angle.
Yeah.
That would complicate the calculations more than I'm willing to do. But you could have an inertial observer and spend some more time there. Yeah.
Someone else could do that and cite you.
That's true.
It wouldn't be possible to do like a flyby like through between like 1 and 2.
Yeah, that's what I was suggesting.
Okay.
Yeah, and you may even be able to go in and do like a few loops and then come out.
Yeah.
But those trajectories are more
That's hard.
complicated. And
Yeah.
Yes.
What causes the squiggles in the power ratio versus scale? Like in
Yeah,
the
that's another
middle
good question.
scale?
So another good observation. Right, so there's squiggles here. What do they come from? So I'm dividing 2 power spectra here, so I haven't actually shown either of the original ones. But there are squiggles actually in both the power spectrum with the Hawking radiation and in the power spectrum without. These come from the baryon acoustic oscillations, which you may be familiar with in the early universe. So on these scales, power spectrum has these wiggles. Due to the baryon acoustic oscillations, if you're not familiar with those, these are outwardly propagating sound waves in the early universe that then became frozen at the epoch of recombination when the photons decoupled from the baryons. And what happens when you add the Hawking relic is this actually has an effect on the baryon acoustic oscillations as well, and it very slightly changes the phase of the wiggles. And so you are dividing by 2 power spectra, both of which have wiggles, but they're slightly misaligned. And then that causes the ratio to have wiggles.
So would you hazard a guess in public as to how this would look for rotating black holes?
Rotating black holes. I don't know. No, I'm not sure. So rotating black holes will preferentially emit particles of higher spins. So there would be a greater spin dependence, I think, would be the main effect I can think of, where higher spin particles from rotating black holes will be preferentially emitted from spinning black holes. And so in some of these calculations here assumed the primordial black holes weren't spinning. You would actually get potentially, you would see stronger effects from higher spin particles. Yeah.
That exact question.
Oh, please.
You'd mentioned like very early in the talk that there had been a previous work that found there was something weird happening at the short sleep radius and you didn't find that. Is the reason you didn't find that because of what you talked about later with you didn't have enough time to measure it, or what was different between their treatment and your treatment?
Yeah, so so we actually both did the same calculation in principle. And one of our motivations for doing this calculation was to study this interesting feature that they found. How come there is a bump in the Hawking radiation and a peak near the horizon? This is very interesting. We should investigate it further. Unfortunately, it seems that there is no such bump, and my hypothesis, we are calculating, precisely the same equations. So as far as I can tell, they had some numerical issue in their code because at the horizon, a lot of numerical issues come about. You get oscillations in these solutions that become infinitely high frequency. And so you have to take a lot of care numerically. And I just think there was a numerical artifact in the prior work, and that our work actually corrects this. Density?
Yeah. If the density of the primordial black holes are high enough, the number density is high enough, could you have a situation in which the relics are decelerated by gravitational interactions with surrounding primordial black holes? So that would produce something that is cold at present day, but were emitted hot, let's say.
That is an interesting question. I haven't considered the effect of deceleration of the particles by I think we are taking that into account, right? Because we are modeling the universe as matter dominated, right, during the emission of the particles. So I think our calculations, in fact, are taking that into account. You do actually raise, though, an interesting question about, is there a way that Hawking relics can be cold at the present day? And the answer there is yes. The way that happens is you ramp up the mass of the Hawking relic super, super high, like way higher than any of the particles we currently know. And those particles are going to be so heavy that they're going to be cold at the present day. The problem is that if you ramp up their mass, then you end up with too many of them, right? You end up with too much energy. You end up exceeding the dark matter. What you can actually do is ramp it up so high that the black holes initially don't have enough energy to even emit those particles. So that the black holes only emit a very small number right at the end of the evaporation when they get hot enough to emit these very large particles. And so you then get a very low number density of very heavy particles that end up being cold at the present day. So there is a way to sort of tweak it, but it's very fine-tuned in a sense. You really have to pick the right parameters because otherwise you're going to mess up the dark matter density. So everything needs to be just right. You need to have like black holes formed at like exactly this abundance initially, and the particle had to have exactly this, and then everything worked out. And if you had perturbed from that just a little bit, you would have just way too much dark matter. So it's a bit more brittle. Yeah, it's possible.
Okay.
So you showed the plot of the Hawking radiation temperature basically as a function of distance from the black hole. And I wasn't surprised it was a falling function. I mean, just naively, someone who doesn't work on general relativity, I would have said that, there's a gravitational redshift as the photons climb out of the potential. And so whatever temperature you would assign to the black hole looking at it at infinity should appear to go up as you get close. But then you showed this expression with a square root of 1 plus this squared plus this cubed. That is not what you would get from that. So there's obviously something much more interesting going on. Can you give us any intuition for, like, without going and reading that paper, like, why does the curve look like that? What's going on?
I mean, John's shaking his head. We don't know.
Well, sorry, you hid this wonderful plot that Chris made. He's too nice. So he doesn't want to like show everyone else's
wrong formulas, but there's like half a dozen versions of that formula. They're all very different.
Yeah.
Oh, wow.
So like one of them was gonna fit and it just happened to be this one.
I see.
Yeah.
The Charles factor, okay.
Avatar.
Chris, great work, and I have a question about this plot as well. It's maybe a little bit technical, but when you do the numerical integration near the horizon, in one respect, it's similar to a shockwave, supersonic shockwave. You don't have kind of the cells next to each other communicate with each other. So, what kind of numerical scheme did you use in this case?
Yeah, so I used, right, so there are quite a lot. I didn't actually show the formulas, but there's actually like quite a few steps in this. First, you just have to numerically, so part of the numerical challenge really is just solving for the basis modes of the Klein-Gordon equation. And that's actually where a lot of the numerical issues arise, because you know, at low energies and high angular momentum, the potential, the gravitational potential ends up with this huge barrier. So that's actually literally just computing those basis modes is where a lot of the numerical issues come in, and those are the ones that oscillate very frequently at the horizon. After that, you then have to combine those numerical solutions into a series of integrals and sums, right? So I use a numerical ODE solver to solve for the basis modes. That returns like an eighth order polynomial approximation to it, and then I used like numerical integrators to integrate functions of those across the horizon, basically. I don't know if that like completely answers your question.
Yeah.
Okay, we're a little past half hour, so I'm gonna cut it off here. Thanks everybody for coming. You should expect an email from me in about 2 hours. We'll have a reception in the lobby. And let's give Chris another